Hi, my name is Steve Ellington. Call is N4LQ, and I live in Charlotte, North Carolina. I've been a ham since 1964. Most of the information that I've gathered over the years has been through experience. I am not an engineer, nor am I an antenna expert, but I have been involved in electronics for a long time. I've put up hundreds of antennas, and my dream antenna has always been a simple antenna that's inexpensive, easy to put up, doesn't take up a whole lot of room, and is easy to match. It does not require a lot of tuning and a lot of adjustment, and provides effective communications both local and worldwide. That's indeed a lofty goal, and a lot of times when we talk about antennas and the characteristics of them, there is always a lot of dispute and controversy, but I hope you'll sit back and listen to what I have to say about this end-fed half-wave multiband antenna. So back in 1909, there was a patent in Germany filed by one Hans Biggerow. His invention claimed that it would keep the antenna at a far enough distance away from the balloon to reduce the possibility of the hydrogen in the balloon from exploding. I'm sure balloons leaked back in those days, and as we know, many of the hydrogen-filled balloons were lost to fire back in those days. I cannot find very much information about transmitters and receivers being carried on balloons in that era, especially spark transmitters, which doesn't seem to me like a very good idea. Yet here we have this invention in 1909. Well, the antenna is number 4 here, and this photograph was actually taken from his patent. The antenna is a half wavelength long. So if you can imagine, if this was a 80-meter antenna, then it would be about 130 feet long, dangling from the end of this ladder line. Where the ladder line and the antenna join would be called the feed point, and the idea is that the feed point would match the antenna. The ladder line would transform the impedance of the antenna, which is very high, to that of the transmitter, which is very low. So that's the invention that he put out there. I don't have a whole lot of information about people using balloons back in those days. I know they used balloons for signaling and for lookouts during the Civil War, and so there may have been some European uses for this. And anyway, it's a good place for an antenna, hundreds of feet above the earth, and I think it's a very viable invention, and we'll see how this evolved to the modern day end-fed half-wave antenna. So this is what happens when high winds hit a balloon, and of course the balloon turned sideways, and Mr. Biggerow found out about gravity. But anyway, this shows us how the antenna could have evolved into a what became known as an end-fed ZEP, which we'll talk about a little bit later. So again, we can see here that the antenna proper is a half wavelength long, as shown, number 4, and the ladder line later became known as the counterpoise, and that provided the other so-called missing part of the antenna, but at the same time it was designed in such a way as to not radiate. So the feed line being number 3 there, and the spacers and the wire composed the feed line, and the idea was that this feed line would not radiate, but the antenna would, and again, it would protect the balloon from exploding. Well, as you can see, Mr. Biggerow has fallen out of his balloon again. This time the balloon is upside down, and we can see more how it became a J antenna. And it was called the J antenna back in those days. And if you look to the right here, you can see how it became known as the J pole antenna, which is a popular homebrew version of a simple VHF, usually 2 meter or 440 type antenna. A lot of times copper pipe is used as the antenna proper. And again, we have our quarter wave section here. The actual spacers are not shown, so it doesn't look like ladder line, but anyway, it has the same effect. So again, the impedance of the half wave antenna is very high, and as you can see here, the antenna itself is a half wavelength, and then it's joined by an additional quarter wave section composed of 2 wires or 2 pipes, and then that matches the antenna. Well, the match is not exactly 50 ohms, and so that evolved into this B drawing here, which shows the feed point just a little bit up from the bottom, and that provides the exact match for our coaxial cable. One disadvantage to this entire concept is that it's only good for one band at a time. So this is not a multi-band antenna. So this is the Graff Zepplin in 1928, and it's widely published that the Graff Zepplin did use this J-type antenna, which became known as the ZEP antenna for that reason. And I have taken liberty to draw what I thought the antenna might look like, but I have a feeling it probably was vastly different. I've done a lot of surfing the internet, and I can't find any information about the antenna. I found some information about the transmitters and about the bands they used. It looks like there was some kind of a wire that went from the tail up to the control room for the radios, but I do know that they were using a wire. There was a lead weight at the end of the wire, and since it was a form of a J antenna, we know that much, then I just drew it as such. Okay, here's the antenna that's been redrawn so that the ladder line is now vertical. It's the same antenna, but now it's starting to look like a real popular ham antenna that was used back in the 30s and 40s. If you read the old antenna manuals from back in those days, you'll always see this antenna. This one is 134 feet long, and the feed line is 67 feet long. And the idea here is that on 80 meters, the antenna is a half wavelength long. The impedance at the end on the far left there is very, very high, on the order of a few thousand ohms. And the ladder line is exactly a quarter wavelength long, and that will transpose the impedance down to something close to 50 ohms, as long as you are on the right frequency. If you deviate from that frequency, then of course it will no longer be a ZEP antenna, and the feed line will become unbalanced because the currents will be out of phase by something other than 180 degrees. The radiation will no longer cancel, and you'll end up with feed line radiation and possibly a lot of RF in the shack. Down at the bottom here we have our formulas for a half-wave antenna. 468 divided by the frequency in megahertz. That'll get you in the ballpark. And the quarter wave section for matching is 234 divided by the frequency in megahertz. And again, this is strictly a single band antenna, because if you try to use it, for example, if you tried to use this on 40 meters, it would be a terrible situation because the impedance at the end of this antenna would be high, but the feed line would be a half wavelength long at that frequency. And a half wavelength feed line will not transpose the impedance at all. Theoretically, you would end up with the same impedance that you started out with. So your transmitter would see an impedance of several thousand ohms, and it would present a very, very bad situation. So it would be the worst possible antenna for 40 meters unless you redesigned it and made the lengths just right for 40 meters. Well, to do that, you should reduce the you could reduce the top part there to 67 feet and then make your ladder line 33 feet. Hopefully that would reach your station. So anyway, it's not very versatile, but it does work great on one band. On this slide, we have a half wavelength piece of wire, which is our antenna, and we're showing the voltage and the current distribution on the antenna wire. The current at the center of a half-wave antenna is always at a maximum, as you can see here. Now I know it's below the baseline here, but that is still maximum. Up here, if it were up here, it would still be maximum because this is just showing part of a sine wave. If you can imagine it just keep on going out into infinity at the ends. The voltage, as shown here, is at the lowest point in the center and the highest point on the end. So you always will find that the voltage on the end of a half-wave antenna is maximum and minimum in the center, and the current is always minimum on the ends and maximum in the center. The impedance is always high at the ends and always low at the center of a half-wave antenna. The impedance will vary slightly when height is changed, but it will always be low in the center. If we feed the antenna in the center, as we do a dipole, then we need low impedance feed line, such as coaxial cable. Unless we use some kind of a transformer, the impedance will always be somewhere around 50-75 ohms. If we feed the antenna on the end, then we will need some kind of a high impedance matching device. The impedance is so high, it's anywhere from 2,000 or so ohms up to 5,000 ohms. It is so high that we must use some kind of a transformer device at the end in order to match it. Even ladder line with a 600 ohm impedance can't match this. It would have to have such a great spacing that it would be impractical. So here we are showing the end and center impedance of a half-wave antenna, 134 feet long, and this one is cut for 3.5 megahertz. It's going to be about 130 feet long, 134 feet, and it's 1/2 wavelength long. Again, the current is maximum at the center, and our voltage is minimum, and voltage is maximum at the ends, and so is the impedance maximum at the ends. So here we are showing the end and center impedance of a half-wave antenna, 134 feet long, and this one is cut for 3.5 megahertz. It's going to be about 130 feet long, 134 feet, and it's 1/2 wavelength long. Again, the current is maximum at the center, and our voltage is minimum, and voltage is maximum at the ends, and so is the impedance maximum at the ends. Well, now here in this slide we're showing what happens when we feed the same antenna, the 80-meter antenna, with a 14 megahertz signal, a 20-meter signal. Well, this time we're kind of back to the old low impedance at the center, but our impedance is still high on the ends. So this would maybe be usable with coax. It probably would be fairly high SWR, but not anywhere near 100 to 1. But again, the advantage of feeding something on the end starting to show again, because our impedance is still high on the ends. So let's talk a little bit about all the different kinds of multiband antennas that we've seen over the years. There are so many different types. There's end-fed antennas, center-fed antennas, there's trapped antennas, multiband verticals, there's loops, there's just an astronomical number of antennas. There's even one that is supposed to cover all the bands with a low SWR because it has a resistor in it. That's a really great antenna, as you can imagine. But probably one of the most common antennas that has ever been used by hams is the old-fashioned doublet antenna. This thing's been around forever, and we talked about it a minute ago. It's a antenna that is usually a half wavelength long at the lowest frequency that we're going to use it. So if we're going to use it on 80 meters, we'd want to make it 130 feet long, or half a wavelength. If we wanted to use it on 160, it would need to be 250 or 60 feet long. The antenna being fed in the center with some kind of ladder line, 450 ohm web type line, or your own homebrew line, which could be up to 600 or 800 ohm with spacing of 6 to 8 inches. It's really pretty stuff, and it's very common. Its disadvantage is that the length of the feed line and the length of the antenna all work together to give us the impedance that the tuner is going to see. And we do have to have a good tuner, because the impedance is going to vary widely. It can vary anywhere from 10 ohms on up to several thousand ohms, and often it goes so far out of range that the tuner can't match it. And when that happens, we have to either change the length of the antenna to compensate for it, or change the length of the feed line. Well, if this feed line were exactly half a wavelength long, remember that a half wavelength feed line repeats what it sees at the antenna. So if the antenna is operating on the fundamental frequency, for example 3.5 megahertz, and the impedance at that center point is 50 ohms, then if our feed line is a half wavelength long, at the other end we will have 50 ohms again. As a matter of fact, you could just plug it right into your transmitter and not even need a tuner. And then when we go to operate on 40 meters at 7 megahertz, our impedance here at the center will be thousands of ohms, and the feed line is going to transpose that to whatever, and then the tuner is going to have to match it. It could very well end up that the feed line would transpose that to a nice impedance. It would be easy to match, depending on the length of the feed line. And so we're always trying to get this thing to work, and it seems like the problem is we always end up with some contrary band that just doesn't want to match. So we snip off some feed line, or we add some more feed line, or make the antenna a little bit longer. And then the other problem that doublets have is that of balance. And unless these two wires are exactly the same height above ground, and both wires are pretty much level and exactly the same length, what we end up with is an imbalance in this feed system. Now the idea here of ladder line is that the currents are opposite and the phases are opposite, and that the phase cancels the radiation from the feed line, and so we don't have any radiation. That's the ideal situation. But I can tell you from experience that if you just drive your car and park it under this side, it will unbalance this antenna, especially on the lower bands. So that is one of the problems, finding the right length for the ladder line, and also that of balance. One solution that has been proposed over the years is to use what they call a current balun at this point, and there are those that claim that the current balun forces equal currents into the ladder line. Well, that it does, but it does not correct for the phase difference, because by imbalance it can't do that. So we're still going to have radiation from the feed line, and hopefully that'll be choked out by that current balun and keep it out of the shack. But from my experience, I have gotten some pretty hot current baluns. Running 500 watts CW, I've seen baluns get so hot that you can hardly touch them. So of course that represents power loss. So this antenna, in one sense, is a tremendous multiband antenna, but it does have some issues. And of course the other issue is that of how do you get the ladder line into the shack, and how do you keep the ladder line parallel to the antenna, or I mean at right angles to the antenna, so that it doesn't cause a phase shift and cause radiation. I mean, you don't want to run your ladder line off at some angle like this under one side of the antenna. You want it to be dangled straight down or straight out directly to the shack. And then of course you don't want your ladder line real close to a rain gutter, and then you have to figure out some way to protect it from lightning. You don't want lightning coming in on it, and that means you need some way to disconnect and ground the ladder line. So all those things have to be considered when deciding to use the doublet antenna. Well, this is the old popular end-fed multiband antenna, and basically it's just a piece of wire, and you have an antenna tuner and a piece of wire of however long you can make it, and the old saw is that the longer and the higher the better. So we come out of a window or something and run it up to the top of the house, and then run it out to the nearest or the farthest tree and get it up as high as we can get it. We're going to need a really good ground system for this antenna, because the ground actually provides the other half of the antenna. If it's a bad ground, we're going to lose a bunch of power in it. And also the impedance that this tuner has to match is going to be all over the map. You never know what it's going to be, depending on what frequency you're on. Again, it could be just like the doublet. It could be anywhere from 10 to 5,000 ohms or more. So that, again, is going to require some trimming and pruning and experimenting, and it may end up that you're not able to use this thing on all bands without actually changing the length of the wire or something like that. Well, here's an old antenna that I've used a lot for multiband use. This is the loop antenna, and if you've got plenty of room and you've got enough supports, I do highly recommend it. I don't recommend running it over your house because that can cause all kinds of problem. I've done that before, and it can set off smoke alarms and burglar alarms, and also the antenna will pick up whatever is in the house, such as your internet connection and your TV set and your electric razor and so forth. So do try to keep the antenna away from the house as much as possible. The loop antenna, basically the ideal situation would be a full wavelength in diameter, and of course it's not usually possible to make it round, so we make them square, and we make them a quarter wavelength on each side. The impedance at the feed point is usually reasonable. We don't see these impedances that are thousands of ohms like we do with the doublet and the end-fed. It's pretty tame. It's usually on the order of anywhere from 50 to 300 ohms. So you can get by with using almost any kind of feed line, from cheap coax to cable TV 75 ohm coax to computer coax at 92 ohms. And I have actually used computer coax. It's around 92 or 100 ohms. It makes an excellent match for the loop antenna. A lot of people use ladder line to feed it. 300 ohm ladder line works fine. 450 ohm works fine. Nothing that you use will have a really super high SWR on it. The antenna can be shaped as a delta or triangle. It can be vertical. It can be horizontal. And it can be a horizontal triangle. That's my favorite, the horizontal triangle. It tends to be a little less directional than the square or quad, which is what I like. With a quad, with a four-sided loop, you get a big, strong lobe opposite the feed point on the higher bands. And that's fine if that's what you want. It sort of becomes a little bit like a small rhombic. And of course the rhombic itself, shown in the center there, that's a form of a loop antenna. So these are great antennas if you've got the room, you've got the supports, and you've got the tuner. You will need a tuner, but again, it's a good overall antenna. As far as DX and stuff goes, the antenna at the low bands, if you make this say a full wavelength for 80 meters, it'll be 270 feet or so around. If it's 30 or 40 feet high, it'll have a very high angle of radiation, so it's great for local stateside stuff. Regional communications is okay. You go up to 40, the angle of radiation starts to go down a little bit, so it's a great antenna for 40. You're going to work out a little bit farther. You'll even work some DX on 40. By the time you get up to 20, the angle of radiation is even lower. So what we find with this, with a horizontal loop antenna at least, is that the angle of radiation goes down as the frequency goes up. And it's pretty consistent about that. With the vertical loop, the angle of radiation can actually start out fairly low on the lower bands, great for DX, but can actually get too high at the upper bands. So there you have it. That's the loop antenna. It's a great antenna. So several years ago, maybe 10 years ago, we started seeing this antenna crop up. It goes by different names, and a lot of people call it the magnetic antenna. They call the UNUN or transformer that is used to match it a magnetic transformer, which sounds really sophisticated. The transformer has a ratio of 9:1. It is a true auto transformer. Your antenna is at DC ground potential at all times, as you can see there. It's good for lightning protection. It does bleed off the static. The question is how long to make it. And it's one of those things where you never are really sure how long to make the antenna. There's a lot of controversy about it. A lot of people sell this system as a multiband antenna, but it's got a lot of problems. First of all, in just about all installation instances, you're going to need a very good ground system, if not radials. Otherwise, you're going to lose a lot of power in the ground. And I see these things advertised as, 35-foot wire covering 160 through 10 meters. Well, there you go. The impedance at the end of a 35-foot wire for 160 meters is going to be way out of range of this poor little UNUN. And by the way, the word UNUN means unbalanced to unbalanced. It's kind of the opposite of a balun. A balun is supposed to convert an unbalanced transmitter to a balanced antenna, or vice versa, balun. And this is an UNUN, unbalanced to unbalanced. And of course, a single wire like this is unbalanced, and so is the transmitter. So it's technically an UNUN. eBay has got a lot of these with different brand names on them. I have one here in the shack called the QSO King, and I took one apart, and it's actually well built, and it's actually a 9:1 UNUN inside, and it's supposed to handle 1,500 watts or something. But now that is not necessarily the case, because remember, if the impedance doesn't match the source, if the impedance of the antenna doesn't match that transformer, it's going to cause a high SWR. Well, this transformer has a 50 ohm input, and 9 times that is 450 ohms. So the chances of that actually matching are not very good. And it's going to take, again, it's going to take a wide range tuner to match this antenna. And from my experience, it's not a very good antenna system. And again, on the 9:1 magnetic balun, here is the schematic if anybody is interested. This shows you how to build one. It's a trifilar wound, 3 wires going around a toroid core, and that's basically showing you how it's wired. And again, it produces a high impedance output, 450 ohms, for your wire connection, and the input impedance is going to be 50 ohms if it sees a 450 ohm load, which it seldom does. So there's a lot of advertising hype out there, and a lot of people get these confused with the end-fed half-wave antenna that we are going to talk about. Okay, one more slide here on the 9-to-1 UNUN, and here's a couple of pictures of these UNUNs. This one is made by Palomar, and so is this one. And this one is called the Bullet. It covers 1 to 31 megahertz, 500 watts PEP, and it's got some random length of wire here for the antenna. Sometimes we call these random length end-fed antennas. This one here is 50 ohms into 200 or 450, so this is like a dual output version of the same thing. And notice we also have a ground or counterpoise tap here on both of these, and you are going to need it because that if it's not setting right at the ground, this wire will radiate profusely just as if it were an antenna. And at the same time, it's going to receive signals. So remember, if you run this thing next to a noise source, you're going to hear it. And lastly, on the 9-to-1 system here, this chart is from Balun Design's website, and it shows the proper length for one of these random length 9-to-1 magnetic balun magic antennas. And as you can see here, the lengths are all over the map. We start out at 53 feet, and the ones in blue are supposed to be the best. And you see here 53 feet, and look here, 124.5 feet is one of the best lengths, they say. 160 through 10 meters. Well, now think about this. 124 feet. What's that? Does that length sound familiar? Isn't that like about a half wavelength, somewhere around 75 meters? So that UNUN is going to see the end of a half wavelength antenna. So what's it going to see? It's going to see thousands of ohms. Interesting. Alternative lengths, in case these don't work, you can try these lengths. It's a little bit hilarious. So we finally made it up to the modern day end-fed half-wave multiband antenna. The first time I ever heard of these things was an article written in QST, March 2016, page 51. So this is a clip of the actual article, and I read this thing, and it said the SWR was reasonably low on every band, 80 through 10 meters. It didn't seem to work on 60 meters. That was a little bit of a problem. 30 was a little on the high side, but of course that's not a multiple. It was up around, I don't know, 3 to 1 or something like that, and they had to use a tuner. But the rest of the bands were pretty low, and the more I read it, I said, this is really strange. Here is an antenna that the ARRL laboratory has examined and done a review on, and they actually ran some tests on it. So here we have the test. This is a clip from the same article that explains how they tested it. It said they didn't have the right instrument to actually measure the highest load, but still it said the power loss was essentially nothing. It says the output power was equal to the input power within the reliability of the less than ideal test setup, indicating minimal loss. That was very encouraging. And they didn't open it up because it was glued shut. They've got screws. The company that sells this thing is the name of by the name of My Antennas. They've got screws holding the lid on, and then the lid was also glued shut. I wished, I mean, for something as cheap as it is, it was like $110 or something. They should have just cracked it open and taken some pictures of it, but I guess they were honoring the privacy of the manufacturer and didn't want to show the insides of it. So anyway, the guy that wrote the article hooked it up, ran it from the side of his house out, made a bunch of contacts, said it worked great. SWRs were good, and I thought, this is so interesting. I have got to get one myself and just find out what's in it. So I ordered one, and it came in, and I didn't bother to even hook it up. I got the proper tools here. I got the screwdriver to take the screws out, I got the hammer, and I got the chisel, and I went to work and then very carefully removed the cover from the transformer and opened it up. And inside I found a stack of 2 toroid cores that were glued together, and a toroidal winding of a primary and a secondary. And it's not quite like anything that I'd seen before, because the primary was twisted and the secondary was not, and it had like 2 turns on the primary and 14 on the secondary. Well, that's a 1:7 ratio, so 1:7. You square that, it becomes 1:50, or 1:49 actually, when you square 7. So our impedance ratio here is 1:49, and that kind of puts the impedance at the antenna jack at around 2450 ohms, which is supposed to match the end of most half-wave antennas, or multiples thereof. So after studying this thing for a while, I wound some of my own and tested them in every which way I could test them. I used different mixes, and that's the important thing, is the mix of the ferrite that is used in this core, and also the diameter of the core. And I did a lot of research, and apparently this design started over in Europe, and those guys over there developed this antenna over the past few years, and I'd say some very, very smart people were in on the beginning of this thing. The guy that runs My Antennas, I think, brought the idea over here to the States and began marketing the transformer, and he makes a very, very excellent product. He sells them at different power levels, and that's mostly dependent on the number of cores that are stacked together. One core would be like for maybe 200 watts or so. 2 cores stacked together would probably handle, depending on what mode you're operating, sideband, it would probably handle close to 1 kilowatt, and 3 cores would handle full legal power on sideband. Not so much power on CW, and even less on the digital modes or teletype. But still, it's very usable for most of us. As you can see here, the primary is twisted, and The wire is 14 gauge is what my antennas use. The European version of this that I've seen put out by what is it? High infed, yeah, high infed antennas. Their wire looks a little smaller. Maybe it's equivalent to 16 gauge. And there's been some recent studies done on wire size and SWR, and it's starting to look like maybe 16 gauge might be a better choice. That's plenty big to handle the current involved here. It's not a whole lot of current. So I'm going to do some more experimenting and find out which one is best. But ferrite is an insulator. It's a ceramic-based material, and I have even used bare secondary wire with no insulation at all wrapped around this thing, and it works perfectly well. So don't worry too much about taping these things up to keep from scratching the wire or something like that, because that's just not going to be a problem. There's some unknowns, like what effect does insulation have on the SWR? Does it help it or does it hurt it? There's a lot to be learned here, and a lot of experimenting needs to be done. Now you'll notice there's a 100 picofarad capacitor across the primary. This where it goes to the transmitter here. That comes into play on 20 meters and higher. Up around 10 meters, it makes a huge difference, and it's absolutely necessary on the higher bands. For the lower bands, you can just leave it off. And we have found that it needs to be a high voltage capacitor. You can get these things up to 15,000 volts. They're tiny little old things. So don't worry about getting too high of a voltage rating. I would not even consider using something rated under 1,000 volts. I don't know why it has to be so high, but I think originally that they were using 3,000 volts, and somebody put a couple of kW on it and blew it, so they went to 6,000. You look inside the my antenna transformer, they've got a couple of 220s in series, and that drops it down to 100, but it doubles the voltage rating. So whatever you can come up with. Here's a part number for Mouser that you can use. You can also get these parts off of eBay. The toroid cores itself, here's a Mouser number that you can use, and the cores are about I think $4.50 a piece, so it's inexpensive to do. The wire you can get on Amazon. Just look for enamel wire. You'll find plenty of it on Amazon.com. So I took a picture of the inside of the my antennas, and maybe a little bit dark and hard to see here, but you can see how they held it inside the case with these nylon clamps. And different manufacturers have different ways of doing that. In my homebrew unit, I don't use anything. The wire is stiff enough to hold it without doing anything, but of course shipping it, it could eventually break loose and cause a problem. MFJ sells a version of this thing. I would steer clear of that one. It is cheap, but it looks like they're using some kind of house wiring to wrap it with. The primary is not twisted, and the first one that we heard of, the guy showed us some pictures of the inside where the wire had broken loose or had never been soldered or something. So the case on it has holes for ventilation on the back, so you have to be sure not to get it upside down or it'll get full of water. So I think I'd steer clear of the MFJ, but the my antenna and the one from High Infed are a good choice. So I started a Facebook group for the end-fed half-wave antenna, and if you just do a search on end-fed half-wave antennas, you'll find it. And we now have way over 4,000 members of this group, and there's a lot of experimenting and trials and errors. People are trying different things, different configurations, different ferrite mixes and different winding ratios, and they publish their results on the group. And of course there's a lot of questions that get answered, and if you're interested, we'd like to have you join it. Here we have a stripped down version of the transformer. This one's under test. The capacitors probably grouped together there to equal 100 picofarads in some fashion, and it just shows you how simple this thing really is. The way we test it is to put a 2,450 ohm resistor between the antenna connection wire and the ground of the coax, and just simply hook it to an antenna analyzer and sweep it across the bands. You'll find that the SWR will stay low from, say, 3 megahertz on up to 28 megahertz. If it's working properly, that's what it'll show. There's usually some point around 11 or 12 megahertz where you get this blip of a real high SWR. That's your resonance point, and there's no band there to worry about, so it doesn't really matter. Now let's look at some ways to install the antenna. Most of us have a small yard, and we're going to look at some different configurations. Here's an aerial view showing the lots or the property of a lot of houses in the area, and you'll notice how these lots are shaped narrow and long, and these are the type of lots that are really conducive to the end-fed half-wave antenna. And this slide is showing a typical center fed and the problems associated with it. Notice that the feed line is coming off at an angle, and it's partially under one leg of our doublet, and that'll cause an imbalance, and this feed line is going to end up radiating. And so this guy here has a city lot that's narrow and rather deep, and he has a tree right behind his house, so he's formed an inverted L, which is an excellent configuration for an end-fed half-wave antenna. His first 30 or 40 feet is going right up to the top of this tree, and then going horizontally across the yard to another tree. And of course this guy here, if he were a ham, would have an end-fed half-wave antenna, and he's able to come out of the back of the house from, say, the top of the roof or something and go way back through the yard and maybe even make this thing a 250 foot long, 160 meter end-fed half-wave. And this fella here is me, N4LQ, and I'm showing here how my antennas are installed. I have a 160 meter antenna that starts at this pear tree in front of the house and goes up to a limb about 50 feet high in the backyard, and then back into the woods, and winds up about 15 feet off the ground, and it's about 250 feet long. And that's the only band that I use this one on. I find it works great on 160 meters. my ground is simply a 4-foot ground rod at the base of the tree, and then the coax goes across the front yard and then into my shack there on the front corner of the house. The other antenna is 80 through 10, so it's 133 feet long, and it starts back there behind the workshop on a 4x4 post that I have, and it's about 2 or 3 feet above the ground where the transformer is mounted. I've got a good ground system there. I've got a couple of 8-foot ground rods, and then I've got some fence wire that I've rolled out going 3 different directions. One of them goes all the way across the backyard to the fence on the other side. The tree is 70 feet high, and that's so that it's vertically 70 feet, and then about 50-some feet going across to a mast, which is actually about 43 feet high on the it's lashed to the deck of the house. Well, I did a lot of experimenting in the backyard with an end-fed half-wave antenna that was cut for 20 meters because it was short enough to be something I could work with, and I got it up there at as high as I could reach because I needed to slide a current meter across it to do the measuring, and I used my little Ten-Tech Corsair there sitting on a wooden table being powered by a battery, so everything was isolated from ground, and I ran it at QRP power, and I was able to set it fairly close there using the little QRP watt meter on top of it. And we ran experiments to measure the effects of counterpoise versus grounds versus no grounds and so forth, which I'll show you in the next slide. Now, here we have the results of the experiment that we did in the backyard, and the major piece of test equipment that we used was the little MFJ 854, and this is a device that measures RF current, and it clamps on the wire, and in this case we used it to measure the current on the coaxial cable and on the antenna and even on the ground. So we know that if wire has RF current on it, it's going to radiate, and we wanted to see how much radiation is actually done by the coax cable versus the antenna. And it would seem logical that we really don't want the coax feed line to radiate. In some cases it would be okay if the coax were up nice and high and in the clear and was in the right direction, then yeah, we could go ahead and let it radiate. So this antenna that we put up, again, is a half wavelength antenna. This right here shows the quarter wavelength points on the antenna, so don't let that confuse you. And here we have our transmitter, and we're simply feeding, let's see, 42 feet of coax to a transformer, which is my antenna is 80 through 10, and then a half wavelength on 20 meters of wire, which was, I believe, about 32 feet or something like that. And we adjusted everything to get the SWR down nice and low, and then we clamped our meter on the antenna, and we measured 180 milliamps at the highest current point, which is right smack in the middle of the antenna where it should be. On the coax, we came over and we measured 40 milliamps at the highest point on the coax. So that part of the coax is radiating, and this transmitter here has no ground at all, so it's all floating. So this is kind of sort of like a dipole in a way, you know, except we have more radiation from the antenna than we do the coax. Our second one down, we're showing the transmitter is being grounded, and that's all we did different, was just ground the transmitter. And now suddenly we have 70 milliamps of current on the coax at the transmitter. Isn't that nice? And then over here on the antenna, our maximum current has gone down to 150 milliamps. Well, that's not nice at all, but that's what happened. And then on our third experiment down here, we took a common mode choke. We actually, I think we used my antenna type choke. It's a real high quality RF choke, and stuck it right against the transformer, and using a double barrel coax connector. And then that should stop all the RF from going onto the coax. Well, maybe, maybe not. The counterpoise, we connected a 4-foot wire and just let it dangle down from the transformer. And then we took our current meter and we measured 20 milliamps of RF current on the counterpoise. The antenna is back to 180 milliamps, which is pretty neat. And our feed line has only got 20 milliamps on it. So, you know, we've got 40 milliamps over here on together. If we add the counterpoise and the coax, they're radiating in some direction, picking up signals and all that kind of stuff. Again, the transmitter is grounded. Fourth experiment down there, we used the common mode choke and no counterpoise. And boy, look at that, 0 milliamps on the antenna. Just a total waste. It just ruined everything. So forget doing that. Don't ever, you have to have some kind of a counterpoise, whether it's your coax or a piece of wire. And it doesn't take much wire, and you don't want too much wire. As a matter of fact, if you had a quarter wavelength of counterpoise wire, then it would probably have about the same amount of current on it as the antenna. And you'd have a dipole. The next one down here, we've got a piece of coax 6 feet long between the common mode choke and the transformer. We ended up with 20 milliamps on it, 20 milliamps between the transmitter and the common mode choke, and back to 180 mils on the antenna. And then finally, we just pulled everything over here to the fence, and we connected the ground lead of my antenna's transformer directly to the ground with a jumper wire. It was screwed right to the fence post, and we hooked it to the fence and to the ground rod that we had there, and the transmitter was grounded to that same ground rod. And look what happened to the antenna current. It went sky high, 240 milliamps. So just by eliminating all this coax and suspended in the air and grounding everything, look what it did to the antenna current. It's just an amazing difference this makes. And we had little, if any, current on the ground lead at all. Now, according to the formula I have up here, I'm showing, basic Ohm's law shows that we should have a total of 316 milliamps of available current. So somewhere we're losing some of our RF, and naturally we're going to lose some in the ground under the antenna. That's our return path, and that's just something that you're going to have that with any antenna. So we came to the conclusion from this that the best way to install the antenna is to simply ground your transformer directly to the ground and then run your coax to the transmitter wherever it may be. Mine just happens to be about 120 feet away or so from the transformer. I'm using good coax. I happened upon some LMR 600, and I can tell you the whole thing works really great. The antenna is 134 feet long, so it comes directly off the transformer, goes up 70 feet, and across the backyard 50 feet. And so that was the conclusion from this experiment, that is the ultimate way to install these things. In this experiment, we put up a 20-meter dipole, and we supported the middle of it with this short fiberglass mast, and at the top of the mast we have a big balun made by DX Engineering, rated for 10,000 watts or something. It's a very high quality current balun, and we put it up as a dipole, and we fed it with this one-to-one current balun. The coax came down to the transmitter, which again is isolated from the ground and everything and being run on a battery. And on the other side of the yard, we put up what we considered a field strength meter, another Corsair 2 sitting on a wood table being powered by a battery, and simply observed the S meter on it. And then we changed the antenna to being an end-fed. Now we did that. If you look real carefully, you might be able to see the my antenna 80 through 10 down there on the left end of the wire. So at the top of the mast, we simply disconnected from the balun and shorted the two wires together, and this became a end-fed inverted V. And we used the fence wire that's across there as the counterpoise for the ground, and measured the field strength again, and turned out to be exactly the same. There was no difference in field strength. So the conclusion there was that an end-fed half wave is equivalent to a center-fed dipole. There's no difference. So we did some modeling using EasyNet. We wanted to find out what the radiation pattern was on a end-fed versus a center-fed antenna installed at the same height. So what we did was model an inverted V that's 22 feet high in the center and 2 feet high on the ends. The antenna is a 40-meter half-wave inverted V, and then we fed 14 megahertz into it to simulate using this 40-meter antenna on 20 meters. So on the left, the results show a high angle radiation when we center feed this antenna, and most of our power is going straight up and being absorbed by the ionosphere. Very bad antenna. Same antenna on the right being used on 20 meters, fed at the end, has an overhead null, so we're not shooting power straight up, and our radiation angle is now at 35 degrees, and it's a very good DX antenna at only 22 feet high. So as you can see, the fundamental frequency of the antenna fed with the fundamental frequency is going to be the same with either antenna. But when we go to the multiples, we start seeing some major differences and some major improvements. The same truth could be had for an 80-meter dipole or inverted V. You could feed it on 40 meters and you'd see some of the same results. It wouldn't be quite this obvious, but you would have less power going straight up and more power at the lower angles on 40 meters while using the same 80-meter antenna. So if you're interested in measuring the power loss of one of these transformers, you're going to need two of them, and you hook them up back to back as so here, and you feed power in from your transmitter through a watt meter. You set your power to some nominal amount, feed it through this transformer into the output of the transformer, from the input of the transformer through a watt meter backwards, and then into your dummy load. And then you take your power difference here and divide it by 2, and that gives you your amount of loss, and then you can calculate the dB loss. Normally the loss would be somewhere around 1 dB or so, which is excellent for a transformer. Well, the 80 meter through 10 meter end-fed half wave is about 133 to 134 feet overall length, and it needs to be that long so it can be used on the higher bands, but it's way down in the CW band, and a lot of people would like to use the antenna on 75 meters. Well, you can use a tuner, but that turns out to be a bit lossy. So one cure that we came up with is to cut the antenna in half and insert a insulator with a capacitor across it. The capacitor is about 300 to 500 picofarads right across the insulator, and you can see in the photograph here where I did the experiment and proved that what this will do is raise the resonant frequency on 80 meters up out of the CW band into the phone portion of the band, and it will not affect the other bands. So the voltage rating on the capacitor should be fairly high. I wouldn't use anything less than 1,000 volt rating, but that's just a little mod there that comes in handy for phone operators who would like to use their end-fed half-wave antennas on the upper end of 80 meters. The 80 through 10 meter antenna is 134 feet long, and we decided to try to use that as a quarter wave inverted L for 160 meters. Well, to do that, it would be necessary to go outside and disconnect the coax and connect it directly to the antenna wire and bypass the end-fed half-wave transformer. And that would make a great 160 meter antenna as long as you have a decent ground system, and I do. I've got some chicken wire and some fence wire laying on the ground and some ground rods and so forth. So I went ahead and tried that, and it worked great on 160, and then I also found that it resonated on 60 meters and on 6 meters. So came up with a diagram here for a relay that is for switching the coax to feed directly to the antenna and bypassing the transformer. The relay that I used I found on eBay somewhere. It's just a 12 volt double pole double throw relay, and I ran some I think it's furnace wire, thermostat control wire to the shack, and I just apply 12 volts from the station's power supply, and that activates the relay, bypasses the transformer, and I'm on 160 then. On the photograph on the right, you can see I've got a 4x4 post. My transformer is on the left, and my relay is in a box on the right. Also, you'll notice up at the top of the transformer a terminal on the left side of the switch box, relay box. You'll see the brown wire, and then there's a disc capacitor going to the top of the transformer box, and that capacitor electrically shortens the antenna when you're using it on 160, it was a bit too long. It was resonating actually down around 1750 or so in the broadcast band. So that'll bring it up, and I believe that capacitor is a 0.0015 picofarad, and that'll take some experiment to get it where you want it on the band, but that really did the trick. And that would go on the schematic, that would go where I show the jumper wire between the relay and the transformer. It would go right there in that jumper wire. So this is one way of doing it, and it works very well. And I'm now on 160, 60, and 6 meters in addition to the other bands. So now we're covering all 11 HF bands with just one antenna.